go over section 7.3 today. That's what I'm going to cover today. And then check daily for 7.4 and 7.5 in modules in Canvas. You know, where you've seen me post the other videos. And then we will meet on, you know, normally we will meet at normal times. We will meet at normal days and times to discuss 7.4, whoops, well, 7.5 and 7.4. So that means have problems ready, have questions and problems ready. Okay. And I will do my best to have 7.4. Oh, I need to spotlight my video. There we go. I will do my best to have 7.4 up tonight. Though I will tell y'all that like last week when for all 4 of my classes, which they're all 4 different courses, I pre-recorded all the lectures since last week was kind of crazy. I pre-recorded all the lectures for all 4 of my classes, and I found that the limit on the number of things that I can record in a day does not come from me just not wanting to record or whatever. It comes from literally my like physical limitations of my voice. Like after recording for like 5 hours straight, my voice just starts to like go, right? And on Mondays and Wednesdays, you guys are my 3rd class that I teach. So you may not see 7.4 up. What I'm saying is I need to let my voice rest after this class, after teaching for a few hours straight. You may not see 7.4 up until either late tonight or maybe tomorrow morning. Okay, so let's get into section 7.3, which is about double angle formulas, power reducing formulas, and half angle formulas. But first, let's review 7.2. So I'll start off by reviewing 7.2 by asking if anyone has any questions from that lecture, or 7.1, but any questions from 7.1 or 7.2 from the video lectures. Okay. I'd like to just work one problem from 7.2. So let's say from 7.2, find cosine of 75 degrees. So recall that 7.2 was about these addition and subtraction formulas. It was about these addition and subtraction formulas. And what they allowed us to do is they expanded from us just being able to find exact solutions for very specific angles, like your 30 degree, 45 degree, 60 degree, and 90 degree angles, or pi on 4, pi on 3, pi on 6, pi on 2 angles. Expanded from that to let us find combinations, either sums or differences of those angles. Things like cosine of 75 degrees. So rewrite this here, find cosine of 75 degrees. Okay, so how did we do that? Well, we note that 75 degrees can be written as the sum of 2 angles, right? 2 distinct angles that we already have information about, 30 plus 45, right? Those are 2 distinct angles there that we know we can find exact solutions for. So we said that cosine of 75 degrees is equal to cosine of 30 degrees plus 45 degrees. Okay, and then we have a formula for a sum, right? That was the whole point of section 7.2 is we had these formulas. And the formula for the sum of two things inside of a cosine function was the product of the cosines of each of the angles, and then minus the product of the sine value at each of those angles. So this is from 7. What happened to my microphone? Are you kidding me? Has it been muted this whole time? Oh, okay, thank goodness. I looked up and it said muted. I thought I'd been muted this whole time. I was like, you gotta be kidding me. They didn't say anything. I've got to say all that again. Okay, all right, so let me back up a little bit here. Okay, so I've noted that 75 degrees can be written as the sum of these two angles. And why did I pick these? Well, because these are special angles that I know how to evaluate inside of a sine and cosine function. And then how did I evaluate each of these? Well, because I recall that, I've got some special reference triangles, like for a 30 degree, 30, 60, 90, I know this side is square root of 3, 1, and 2. That's a 1 right there. That's a 1. Okay. And so this told me that cosine of 30 adjacent over hypotenuse is square root of 3 over 2, etc. So you can do that for each one of these, get an exact solution. And then all that remains at this point is to do your, some arithmetic here. And that's going to be square root of 6 over 4 minus square root of 2 over 4. And then I can say square root of 6 minus square root of 2 all over 4, the same denominator, so I can squish these fractions together. That's as far as I can go. I can't take the difference of these two roots because they're different kinds of roots. Okay. So this is kind of like the crux of 7.2. Where did this formula come from? Well, if you've watched the video, then there's 3 of them, right? There's 6. 2 for sine, 2 for cosine, and 2 for tangent. And they allow us to find exact solutions, which are going to tend to look kind of wild like this, for cosine, sines, and tangents of weird angles, as long as you can write the angle as the sum or difference of two nice angles. So that really opens up all the possibilities. All the possibilities for finding exact solutions from trig functions. So that is just a real quick recap of 7.2. Let's talk about now 7.3. So officially starting 7.3 now. This is all about these new formulas. What is even the name of the section is just double angle, half angle, and product sum formulas. We're not going to worry about sum to product or product to sum formulas. So I'm going to call it double angle, half angle, whatever, and power reducing formulas. Now, this is the point where in trig you are given a ton of formulas, and maybe your instructor might decide to derive a whole bunch of them, or you just work a lot of problems. So I'm erring on the side of working a lot of problems. I don't think that you're going to benefit, honestly, from me deriving these things. They're not hard to derive. The sum formulas, or rather the addition and subtraction formulas from 7.2, those are tricky to derive. And these, though, these new formulas, which I'm going to go ahead and write down, at least the first set, are coming straight from they're coming straight from the formulas from 7.2. So honestly, I don't think you're going to gain anything from me deriving them for you. So I'm going to write them down, talk about them, and then we're going to do problems with them. All right, so if I have some situation where I'm trying to evaluate some input, and the input is doubled like this. So I've got some angle and it's doubled. Then I have this formula for sine. I have sine of 2x is equal to twice of the product of sine and x at the angle that was doubled. I have a bunch of stuff for cosine of 2x. I have 3 different formulas for cosine of 2x. And oops, the reason I have 3 different formulas for cosine of 2x, it's just a consequence of the, oops, let me make sure I write this down right. It's a consequence of that addition subtraction formula for cosine from 7.2. It's just they the formulas are such that it allows us to write down 3 different forms of the cosine of 2x formula here. Okay, and then I have my tangent of 2x, which always looks a little bit different. These formulas for tangent always look a little bit more involved. Okay. There are my double angle formulas. Sine of 2x, cosine of 2x, and tangent of 2x. So what are these useful for? Well, to be honest, in my experience, these are just like nice things to know. Do they tend to be super useful? In my experience, not really. I have not really used them a whole lot, but they're nice to have on hand. And one way that that we're going to work with them is I'm going to give you like the cosine of x or the sine of x or the tangent of x, and then ask you to find each 3 of these. So the problems I'm giving you in this case are not really like going to be good motivation for why we use these. It's just going to be straight up like practice using them. Now the other formulas, power reducing formulas in particular, those do become really useful, especially when you take calculus. You'll use them all the time. So here we go with example 1. Example 1, let's just say if cosine of x is equal to -2/3 and x is in quadrant 2, find, let's see, cosine of 2x, sine of 2x, and tangent of 2x. Something you should note. The sine 2x formula depends on both sine and cosine. The cosine 2x formula can depend on both sine and cosine, or it can depend on only sine, or it can depend on only cosine. The tangent 2x formula depends on tangent. What do we have here? We only have cosine, right? We only have cosine. So does that mean we can only find cosine of 2x? Could we use this to find cosine of 2x, since this is the only one that depends only on cosine? Well, yes, that's true, but if we know this, if we know cosine, the output of cosine of x, and we know x is in quadrant 2, then I can find sine and tangent. And how do I do that? I say, well, if I have cosine of x equals negative 2/3, then that means I have some triangle, and if I just kind of ignore the signs, right, ignore the sign on 2 and 3, on the minus sign, I know that there's some triangle that has an adjacent side of 2 and a hypotenuse of 3 with some angle x. Some angle x. Cosine of the angle x gives me a 2/3, adjacent over hypotenuse. That's how I'm coming up with that. And I'm not really worrying about the sign, right? I'll worry about the sign afterwards. So can't I find this missing opposite side, right? I can find this missing opposite side by saying 2 squared plus, b squared is, Pythagorean theorem here to find that missing side of the right triangle. I'm getting b squared should be 5. Just kind of skipping some steps here. So b is plus or minus square root of 5, really, but I'll say square root of 5, and then I'll decide whether sine and tangent should be positive or negative based off of the quadrant information I was given. So now I can say sine of x is equal to square root of 5/3, opposite over hypotenuse, And should it be positive or negative? Well, it should be negative. Wait, where's quadrant 2? It should be positive. Sorry, I glanced at this and I thought that was like a V, like quadrant. Anyways, that doesn't make sense. So anyways, quadrant 2, it's positive. It's positive. So let's make a note that this is positive in quadrant 2. Sine is positive in quadrant 2 because sine is associated with like a y value, right? Y values are positive in quadrant 2. I also know that tangent of x is equal to opposite over adjacent, so I'm getting square root of 5/2. And tangent is going to be negative in quadrant 2, right? So negative in quadrant 2. Good. So now I have all of the pieces that are going to let me build up these sine of 2x, cosine of 2x, and tangent of 2x. So any questions about that? Because that's the important first step of this problem, is finding from just cosine of x and the quadrant information, finding sine and tangent. So any questions about where I got any of those numbers? For the three of you that have stuck around. Okay. So I have sine of x equals square root of 5/3. I have cosine of x equals negative 2/3. And I have tangent of x equals negative square root of 5/2. Okay. Sine of 2x is equal to twice of sine x cosine x. So that means I'm going to say twice of square root of 5/3. That's a square root of 5. That's a really ugly square root of 5/3. And then times cosine of x, which is negative 2/3. So it's going to be negative. Positive, positive, negative, so it's negative. In the top, I'm going to have 4 square roots of 5, and then in the bottom, I should have a 9. Cool. Okay, any questions about that? I'm going to go ahead and start writing the second one while you think about any questions. Okay, now in this case, cosine of 2x, I have options, right? I have options here. I have these 3 formulas. Definitely, probably not going to use the first one because it just looks more complicated, right? It's got cosine squared and sine squared. So I think I'll use this one. Does it matter though? No, it doesn't matter. It doesn't matter. Okay, so I'm going to have twice of cosine squared, which is negative 2 over 3 squared, and then minus 1. So that's twice of 4 over 9 minus 1. That is 8 over 9 minus 1. That's going to be negative 1 over 9. Good. Okay. So I encourage you to try maybe a different form of the cosine formula and make sure you can replicate that answer. Okay, now tangent of 2x is twice of tangent of x all over 1 minus tangent squared x. Oops. So I have tangent. Oof, there we go. Tangent is negative square root of 5 over 2. So that's what this is what I'm going to be using. This is what I'm going to be using for this formula. So I have twice of negative square root of 5 over 2 all over 1 minus negative square root of 5 over 2 squared. So when you see tangent squared like that, or cosine squared or sine squared, that means you take the output of like tangent x and you square it. That's what I'm doing here. Okay. Now I'm going to have in the top just a negative square root of 5 because the 2 and the over 2 cancel up there. And then in the bottom, I'm going to have 1 minus 5 over 4. Squaring, the negative is going to go away inside, right? And then square root of 5 squared is 5, and 2 squared is 4. So now I'm going to have negative square root of 5 over 1 minus 5/4 is the same as negative 1/4. It's like 4 over 4 minus 5 over 4. That's giving me, that's the same as square root of 5 times 4 over 1. The negatives, I'm going to go ahead and say the negatives cancel, right? Negatives cancel. And if I'm dividing by a fraction, that's the same as multiplying by its reciprocal. In other words, I get 4 square roots of 5. Note also that tangent of 2x, tangent of x is equal to sine over cosine, right? Tangent of x is equal to sine x over cosine x. So tangent of 2x is the same as sine 2x over cosine 2x. Does that check out here? Well, I had sine of 2x being negative 4 square root of 5 over 9. And then over cosine of 2x, cosine of 2x was negative 1 over 9. So how does that work out? Well, the negatives cancel, and I have 4 square roots of 5 over 9 times the reciprocal, right? If I'm dividing by a fraction, I multiply by the reciprocal, so times 9 over 1, and I end up with 4 square roots of 5. So in a problem where you're asked for sine of 2x, cosine of 2x, and tangent of 2x, if you would like to bypass using this tangent of 2x formula, then you can just fall back on relying on this relationship. You know, your arithmetic has to be strong, right? You got to know how to deal with fractions over fractions, but that's okay. This is how you deal with it. You just say this fraction multiplied by this fraction upside down. That's all I did here. Well, I also said that negative over negative is positive, right? I hope you see that as well. Okay. So you see what about the motivation for these formulas. These problems aren't really good motivation, in my opinion, for using these double angle, because the only reason we're using the double angle formulas is because I basically just said use the double angle formulas, right? So I find it hard to motivate this section, really these two sections, other than just saying it opens up a lot more problems for us to practice. All right, example 2. Let's do a similar one. So if tangent of x is equal to -4/3, and x is in quadrant, let's say, where do I want to, just let it be 2 again. Oh, sorry, x is in, you may not be familiar with that notation, x is in quadrant 2. Find sine of 2x, cosine of 2x, and tangent of 2x. All right, first step is to, ignoring the sign, draw a triangle with some input, or a right triangle with some angle input x there from the, or rather the angle from the trig function is x, and then I'm writing opposite over adjacent, so that what I'm doing here is I'm saying that if you tell me tangent of some angle is equal to -4/3, then that, hang on, what's my camera doing here? Let me scoot it up a bit. Then that means there exists a triangle with input x with side lengths like this. Does that mean the exact this is the exact triangle where this came from or something? No, it's some scalar multiple, but let's not get into that. This is a little bit informal, writing it like this is what I'm saying, and ignoring the sign and everything. But it can get us there. It can get us to finding the other sine x and cosine x, the other trig functions. So who knows what the hypotenuse should be? Any ideas? Because that's what I'm looking for here, right? Trying to find that missing side of the triangle. Bailey, any idea what the hypotenuse of this triangle would be? Haley or Braden, any idea what the hypotenuse of this right triangle would be? Yes, thank you. It is 5. It is 5. It's a 3, 4, 5 right triangle. So this lets me say that sine of x is going to be 4/5, and is sine positive or negative in quadrant 2? Well, sine is positive in quadrant 2, so I'll leave it be. And then cosine of x should be adjacent over hypotenuse, 3/5, and it's negative in quadrant 2. There we go. So now I've got all 3 of my trig functions because I already knew tangent, right? So now I'm going to say sine of 2x, sine of 2x is equal to 2 sine x cosine x, 2 times 4/5 times -3/5. A little bit of fraction work here, getting -24/25. Cosine of 2x is going to be, how about I use this one this time, just to mix it up. I'll use cosine squared x minus sine squared x. That's going to be -3/5 squared minus 4/5 squared, which is 9/5 minus 25, sorry, 9/25 minus 16/25. So I'm getting 9 minus 16, 9 minus 16 is -7. Okay. Now, tangent of 2x is, how about just, since I'm asked to find, I was already asked to find sine of 2x and cosine of 2x, I can just, as I said before, just fall back on like the definition of tangent, that tangent is equal to sine over cosine, and as long as those inputs match 2x, 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 then I'm good. And I can just say, well, sine of 2x was negative 24 over 25. And let me write it here to give myself some more room. Cosine of 2x is negative 7 over 25. So that's going to be the same as negative 24 over 25 times 25 over 7. And that's giving me, oh, negative, sorry. And that's giving me 24 over 7 positive. And of course, you could still use the tangent of 2x double angle formula I gave at the top of the lecture and just plug in tangent of x equals negative 4/3. You could do that as well, but I think this tends to be a little bit easier. If you're asked to find sine of 2x and cosine of 2x, then you can use them, right? You can use them in that final step to find tangent of 2x. All right. Example 3. Now, what if we have like a secant function given? If secant of x is equal to 2, and x is in, let's do quadrant 4, find sine of 2x, cosine of 2x, and tangent of 2x. It's going to go exactly the same. It's going to go exactly the same. We're going to build a triangle based off of what we're given. Then we're going to find sine, cosine, and tangent. We're going to decide what their signs are based off of the quadrant. And then we're going to use the formulas. Well, I dropped my red marker, so there it is. Okay. Secant, I know, is equal to, so secant of x by like the opposite over hypotenuse, hypotenuse, adjacent, you know, those three items, like what is secant in terms of that? Well, secant is the reciprocal of cosine. So I should have hypotenuse over adjacent here for secant. So if it's 2, then that means the hypotenuse is 2 and the adjacent side is 1, right? Because 2 can be written as a fraction of 2 over 1. So I need this side, that opposite side. So I'll quickly find it. 1 squared plus b squared is equal to 2 squared. B squared is going to be 3. B is going to be square root of 3. Okay, that tells me that sine of 2x, or sorry, sine of x is equal to opposite over hypotenuse, and then I go back and look at which quadrant I'm supposed to be in. The x angle is in quadrant 4. Sine is supposed to be negative there. Cosine of x should be 1/2. 1/2. And in quadrant 4, cosine of x, in quadrant 4, cosine is positive. And then tangent of x should be opposite over adjacent. In other words, just square root of 3. And tangent should be negative in quadrant 4. There we go. There's the 3 building blocks that we need in order to be able to use, or to be able to find sine 2x, cosine 2x, and tangent 2x. Sine of 2x is 2 sine x cosine x. Sometimes some of the problems with this section and the last section is that there are too many formulas. It's like the toolbox becomes too big and students don't know maybe where to start because there's too many options. Something that I like to point out is that, or you might notice that I'm doing here, is I'm always starting with sine of 2x. And why am I doing that? Well, because sine of 2x only has one option. Like there's only one way to find sine of 2x. Well, at least in terms of these formulas. Right, so that's a nice place to start, just to kind of anchor you to the problem. What am I going to end up with here? One of the 2's will cancel with that 2, and then there will be another one. So square root of 3 over 2. That's interesting. It just ended up being exactly what sine of x was equal to. That's a consequence of this being a special angle. This is, you may recognize these fractions, these outputs. We got square root of 3 over 2, 1 over 2. This is a an angle. This is a either pi on 6 or pi on 3 angle in quadrant 4, and if you double it, you'll get another pi on 6 or pi on 3 angle. Okay. Cosine of 2x. So now you get into this problem where you're like, which formula do I use? Well, just pick one. Don't think about it too hard. Just like write one down. And if for whatever reason it's a wrong choice, which there is no wrong choice when you set it up like this, but if you do pick the wrong one in any kind of problem, then just pick a different one. So 1 minus sine squared. Sine is negative square root of 3 over 2, and then I'm going to square it. So I'm getting 1 minus the negative inside gets absorbed by the squaring, squaring it, and then square root of 3 squared is 3, square root of 2, or sorry, 2 squared is 4. So then I have 4 over 4 minus 3 over 4 is 1 over 4. Something doesn't seem, that should have been, well, if you're paying attention, you see I wrote the formula down wrong. Yep, whoops, need a 2 right here, need a 2 right here, and that means needed a 2 right here. So I should have 1 minus 3 over 2, which is giving me negative 1/2. There we go. So when I double this angle, it ends up like very similar to what cosine gave me, but I end up from quadrant 4, I end up in either quadrant 1 or 2, depending on what, well, in quadrant. Well, it depends on what the angle is, where I would end up, but I end up somewhere where cosine ends up yielding a negative value. Okay, let's do tangent of 2x now. Tangent of 2x. And I'm going to use the formula, not the definition of tangent like I did with the last one. I'll actually use this formula, 1 minus tangent squared of x there. So I'm getting twice of negative square root of 3 all over 1 minus negative square root of 3 squared. That's giving me negative 2 square roots of 3 over, so that's the numerator there, over 1 minus 3 squared. Negative 2 square root of 3 over, oops, no, it's already squared. 1 minus 3, just 1 minus 3. And that's going to be a negative 2. And then finally, I'm getting just a square root of 3. So it's no coincidence that all these answers ended up looking really similar to just what, like sine of 2x was exactly the same as sine of x. cosine of 2x was exactly the same as cosine of x, except different by a sign. Tangent of x was exactly the same as tangent of 2x, except by a sign. And that's just because the angle x in this case is a special angle, and when you double it, you end up back at another special angle. That's what's happening. Sometimes the signs are changing because we're ending up in different quadrants, but it's the same type of angle. Okay. I think that's enough double angle stuff. Let's look at power reducing formulas. These will be super helpful when you go on to take calculus. When you try to differentiate functions that are composites of each other, well, compositions of functions, it's not really a big deal. You learn the chain rule, which if you've taken, maybe you know what I'm talking about, maybe not, it's okay. That's not a big deal. But when you try to anti-differentiate, in other words, when you try to integrate compositions of functions, you get into some issues. And one of the ways to deal with that with trig functions, in particular when you have a squared function composed with a trig function like this, sine squared of x, is to use a formula that reduces the power so that you're not dealing with squared trig functions. So let me write these down and I'll talk about them a little bit. So all three of these, when you square a trig function, you're ending up with it. You're ending up with a with all of them in terms of cosine of 2x. Cosine of 2x, okay? And you'll find, like I said later on in calculus, that dealing with something where the input is being messed with is much easier than dealing with something where the whole thing is being messed with. Like this is the on this side, it's like the entire trig function has been squared. And over here on these sides, it's just the input of the trig function that's been doubled in this case. You'll find that it's much easier to deal with things like this than it is to deal with things like this. And a lot of your integration rules that you learn in calculus have to do with getting things, dealing with things that are, composites. Well, how do I say? Anyways, this is one of the big techniques that you'll see being used a lot. So let's do examples with them. Let's see. But it is interesting how they're all in terms of cosine, right? They're all in terms of cosine of 2x. And we could see this if we derived them, we could do that, and in fact, they would just come from, where would it come from? You could you may need, actually, I don't remember the last time I've derived one of these. I actually don't remember how it goes. We may not have all the tools yet, but we're not going to do it anyway, so it's not a big deal. The book derives a few of these. It doesn't derive all of them. If you'd like to see like these things derived where they come from, you could definitely find it on YouTube. Or that could be a question that you ask too in Wednesday's meeting when we're just kind of meeting and discussing the trig and everything. You could ask me to derive these, and I'll do it for you. I don't have any problem doing that. I just don't want to take up like lecture time doing it. Okay, so all the questions that you're going to be asked when you're dealing with power reducing formulas are going to be expressed something like this. they'll give you express blah, 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 with where there are exponents greater than 1. And then it'll say in terms of first powers of cosine. So the idea is to get rid of all exponents. Get rid of all exponents. That's the idea here. So what I'm going to say is that sine squared x, cosine squared x, well, from my formulas over here, I'm getting 1 minus cosine of 2x all over 2 times 1 plus cosine of 2x all over 2. Okay, now I am going to back up my equal sign because I'm going to need a little bit more room here. Okay, well, at least the denominator is easy. 2 times 2 is 4. I can do that, no problem. Now in the top, I'm going to have 1 times 1. That's the first term. Then this 1 times positive cosine 2x, so that's positive cosine 2x. And then negative, no, moving on to this term, negative cosine of 2x times 1 is negative cosine, of 2x. Hang on. Okay. Good. So it's like a difference of squares, right? Now negative cosine 2x times positive cosine 2x gives me negative cosine squared of 2x. All right. Let's clean this up a bit. Middle terms cancel, and I just get 1 minus cosine squared of 2x all over 4. Now I'm not done, right? I'm not, excuse me, I'm not done because cosine squared, that's a problem. I need it in first powers of cosine, but this is squared. But that's okay because I have a formula over here that tells me how to reduce the power of a trig function. Now I need to note that my input here is 2x. So note over here in the formulas, what happens to the input of x? As you cross this equal sign, you get, there's a 1 plus blah, 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 and there's a divided by 2. But also the input gets doubled, right? You go from x to x, x to x, x to x to x, right? So here, when I use the power reduction formula on this thing now, where the input is 2x, then what I end up with, hang on. Let me do this on fresh page here. I'm gonna have to double this input again. Okay, I'm gonna have to double this input again. Let me write it in blue to make it stand out. So the cosine squared of 2x is going to turn into, according to this formula up here, 1 plus cosine of 4x all over 2. See it turning into that. Okay, good. Now you may say, oh, how do I deal with this, right? How do I deal with this? Well, keep in mind that you can split this fraction up. This is the same as 1 over 4 minus 1 plus cosine of 4x over 2 over 4. Which still doesn't maybe look that much better, but this is the same as 1 over 4 minus 1 plus cosine of 4x all over 8. When you have, remember, this would be like, you could, let me do that off on the side in case you're still wondering where that 8 came from. 1 plus cosine of 4x over 2 times, and then so instead of dividing by 4, I'm multiplying by its reciprocal. That's where the 8 is coming from in the denominator, because 2 times 4 is 8. Good. Now it's in a single power of cosine. That's exactly what I wanted. It's not squared anymore. The last thing I can do is just clean up this fraction a little bit by getting a common denominator. I'm going to want to make sure I know that I'm subtracting the entire the other fraction. You know, when you push the fractions back together and you've got a minus sign, you got to make sure that you're subtracting the entire numerator. In other words, wrap it in parentheses so you don't forget to distribute that minus sign. So I end up with, and by the way, the 2 came from making 1/4 have a common denominator, right? 2/8. So I end up with 2 minus 1 minus cosine of 4x all over 8. Finally, I have 2 minus 1 is 1. 1 minus cosine of 4x all over 8. That's tricky, but you will do things like this in calculus as a intermediate step in integrating something, or yeah, well, really that, yeah, integrating some, you know, sine squared, cosine squared function. Unless you're not taking calculus, then you will probably not see these again very much. Okay, so there it is. It's fair bit of algebra happening there, I guess, with the fractions and whatnot. Probably warrants some more practice. If you know that you are going on to calculus, you may want to practice things like that a little bit more. Example 5, I'm going to say same instructions as example 4, but for sine to the 4th of x. So I have sine to the 4th power. I know that sine squared of x is equal to 1 minus cosine of 2x all over 2. So I'm going to have sine to the 4th of x is equal to sine squared of x times sine squared of x. Right, that's the first trick to this, is pulling apart sine to the 4th as sine squared times sine squared. That's going to be 2 of these, so 1 minus cosine of 2x all over 2 times 1 minus cosine of 2x all over 2. And now it's going to go kind of similarly to the last one, except that it's not like a difference of squares where the center terms cancel out. So I'm going to go ahead and just jump to the product of the numerators here. I'm going to have 1 minus 2 cosine of 2x, and then plus cosine squared of 2x. That'll just come from distributing that 1 times 1, 1 times negative cosine 2x, negative cosine 2x times 1, and then the final product, negative cosine 2x times negative cosine 2x. Simplified, cleaned up, this is what you end up with. Okay, this is the problem, right? The cosine squared of 2x. That's still squared. I need to deal with that, right? So what I'm going to do in order to kind of get around some of this nasty fraction business, I'm going to go ahead and split this up into 3 distinct fractions. And that might help deal with the fraction nonsense a little bit. Okay. And I'm not going to like simplify the fractions or anything. I don't want to do that because I'm probably going to end up having to get a common denominator in the end anyways. So I'm not going to mess with that yet. Now here, my cosine squared of 2x, cosine squared of 2x, I'm applying the formula for power reduction to cosine squared of 2x, which I know is supposed to be 1 plus cosine of 2x, but I have to, the point is that I double the input, so it turns into a 4x, just like last time, and it's all over 2. Okay, now I end up with 1/4 minus 2 cosine of 2x all over 4 plus 1 plus cosine of 4x all over 8. Oh. Well, everyone has dipped out except for you, Braden. Braden, are you still here? Okay, well. At this point, we get common denominators. Common denominator must be 8. 8, so this turns into 2. This first one turns into 2. This will turn into 4 cosine of 2x. And then plus 1 plus cosine. So I don't need to change the last numerator because it already had the common denominator of 8. And finally, I'll just combine my like terms. 2 plus 1 is 3, and then minus 4 cosine 2x, and then plus a single cosine of 4x. And those cannot be added together because they are not like terms. That's an 8 in the denominator there. All right, that is the power reduction formulas. That is the power reduction formulas there at work. Some trickier examples. I think the examples in the homework are not nearly that tricky. Maybe one or two, but all right. Half angle formulas. These are a little bit weirder. But they're coming straight from the power reduction formulas. So if you wanted to, you could derive these on your own. Just plugging in that u over 2. Oops, oh, dang it. I didn't mean to write that. Tangent of u over 2 is 1 minus cosine of u all over sine u, or conjugate paired sine of u over 1 plus cosine of u. All right. So these are for if we, these are a bit more going to act a little bit more like the formulas that we had in section 7.2, where I'm going to actually give you angles to compute, unlike the double angle and power reducing formulas, where we kind of just manipulate the formulas and practice using them. But these are actually, you're going to see they're specifically, they're very useful. And the idea is that your input is half of some special angle that you know about. So let me give you an example. Oh, by the way, the plus or minus depends on where the angle u over 2 is. So remember, u over 2 is just some angle here. Why is it the number u? Why isn't it x anymore? I don't know. That's just how everyone writes them. It's literally like different letter S and T for addition subtraction. It was X for double angle and power reducing formulas. It's U for the half angle formulas. I don't know why the book keeps changing inputs. That it doesn't matter. So U over 2 is an angle here. And in these two cases, you see a plus or minus happening. That is going to be dependent on wherever U over 2 ends up. Okay, so let's run an example. Six. Find the exact value of 22.5 degrees. So this example is a little bit different than the previous ones. I'm actually asking for the value of an angle. So this is more like the questions from section 7.2, where I asked you for the exact value of some specific angle, some weird angle, right? This is a weird angle, 22.5 degrees. First thing we should note, though, is that it's not that weird, because we know that 45 degrees divided by 2 is 22.5 degrees. So that means, so our U value in those formulas is going to be 45 degrees. Why do I say that? Well, sine, remember the formula is sine of U over 2 is equal to plus or minus square root of 1 minus cosine of U all over 2. So the whole U over 2 is equal to 22.5 degrees. That means U must be 45 degrees. Another way to look at that is to say, U over 2 is equal to 22.5 degrees, right? Just lining those up, and then solve for U. Well, how would you solve for U? You multiply by 2 on both sides. There, U is 45 degrees. It's another way of looking at it there. All right, so now I'm ready to plug in, though, because I have sine of 22.5 degrees is going to be square root of 1 minus cosine of 45 degrees all over 2. And is it positive or negative, right? Because it's plus or minus. Well, where is 22.5 degrees is in quadrant 1. So this is positive. So we can write down, this in quadrant 1. So it's positive. All right, now I know that cosine of 45 degrees is square root of 2 over 2. And then this is all over 2, just like that. So radicals and radicals, but it's all right. We're not going to do too much with it other than just kind of clean this up a little bit. How about I take this off on the side, this inside, so I have 1 minus square root of 2 over 2 all over 2. That's the same as 2 minus square root of 2 all over 2 in the top, and then all over 2 there, right? Just this 1 is 2 over 2, and then squish those fractions together. So this numerator compacts into this. And then that's the same as 2 minus square root of 2 all over 2 times the reciprocal. So instead of divided by 2, the reciprocal, the product of the reciprocal there. And then I'm getting this thing. That's going to be 2 minus square root of 2 all over 4. All under a square root. That's going to give me square root of 2 minus square root of 2 inside that numerator, and in the bottom I end up with just a 2, because square root of 4 is just 2. So a lot of these things, if you have the formulas in front of you, then plugging into the formula is not hard. But the algebra does get a bit tricky, right? The algebra does get a little tricky, so you got to make sure that you're practicing that. By the way, that's the final solution there. Okay, example 7. find the exact value of cosine of 3 pi over 8. Well, I know that u over 2 is equal to 3 pi over 8. So that means that u must be, if I multiply by 2 on both sides, then u is going to end up being 3 pi on 4. So my formula for cosine of u over 2, in other words 3 pi over 8, is equal to plus or minus, which I'll decide whether it's going to be plus or minus in a second, 1 under square root 1 plus cosine of u, where u is 3 pi over 4, all over 2. And then I'm thinking about, okay, where is u? Where is u over 2? Where is this? 3 pi on 8. 3 pi on 8 is in quadrant 1. You could convert it to decimals. I mean, not decimals. You could convert it to degrees if you'd like to really decide where 3 pi on 8 is, but I'll just go ahead and tell you this is in quadrant 1. How do I know that? Well, 3 pi over 8, it's less than pi over 2, right? So it's got to be in quadrant 1. It doesn't pass that y-axis. Now, I also know that cosine of 3 pi on 4 is negative square root of 2 over 2. So that ends up in there. So I end up with the exact same thing as the last time. It's going to be 1 minus square root of 2 over 2, and I'm not going to walk through all that algebra again. The answer was square root of 2 minus square root of 2 all over 2. Lots of 2's happening, and they're all buried under no radical, 1 radical, 2 radicals. So ended up being exactly the same. And why is that? How did this end up being exactly the same? Well, 3 pi on 8 is 22.5 degrees. And we know that the sine and cosine agree at pi on 4 angles, right? At pi on 4 angles. Wait, is that right? Hang on. 3 pi on 4, 3 pi on 8, if we convert that, here, let's wait. I've messed something up. Let's see. If we convert 3 pi over 8 times 180 over pi, we get 3 times 180, right? 3 times 180, and then divided by 8. Sorry, yeah, it's 67.5 degrees. No, so this is wrong. It's 67.5 degrees, but it's still like half of a pi on 4 is the point I was trying to make. That's why it worked out to be exactly the same. Okay. Last example with a hang on. What have I done back here? This is I'm having a brain fart. Let me think about this. 3 pi on 8. Yeah, it's still in quadrant 1, so it's still positive. Okay, never mind. We're good. Final example. Example 8 is same instruction, so find the exact value of tangent of 15 degrees. I see that u over 2 is 15 degrees, so that means that u must be 30 degrees. And my formula for tangent of u over 2, sorry, did I say t earlier? I meant 2, is equal to Right, now I have options here. 1 minus cosine of u over sine u, or sine u over 1 plus cosine u. I'll just use this one. It's the first one I wrote down, so I'll just use this. So I'm getting 1 minus cosine of 30 degrees over sine of 30 degrees. So that's going to be 1 minus square root of 3 over 2 over 1/2. So fraction arithmetic here, I'm getting 2 minus square root of 3 all over 2, just getting a common denominator in my numerator, and then I'm going to multiply by the reciprocal of this. Instead of divided by 1/2, I'm multiplying by 2 over 1, and equals. I end up with these 2's canceling, so I end up with 2 minus square root of 3. That's the answer, 2 minus square root of 3. All right, that is 7.3, and 7.4 will be up soon in Canvas.